A particle is moving along a straight line with varying velocity. Our interest is to find its instantaneous acceleration. If Vi and Vf are the velocities at two different instants of time, Vf minus Vi by delta t, say this is the velocity at t and this is delta t later at t plus delta t. So in delta t, velocity changed from Vi to Vf along the same straight line. So Vf minus Vi by delta t would give us the average acceleration. So Vf minus Vi by delta t will give us the average acceleration. If you want instantaneous acceleration, then you'll have to make the interval smaller. The delta t must be made to tend to 0. So if this is say Vf and this is Vi, say this is Vi, this is Vf, this is our delta V, the change in velocity. If you consider smaller intervals of time, this Vf tends to Vi, this delta V becomes smaller, and since delta t also is smaller, we find that delta V by delta t as delta t tends to 0 gives us what you call instantaneous velocity. After all, instant is a duration which tends to 0, very small duration. That's the definition of our instant, right? Instant is like a point on a straight line, and if you're asked what is a point, you would say it's a length element which tends to 0. So delta V by delta t, well, as delta t tends to 0, if that calculation is made, we get instantaneous velocity. We now have a case where velocity is changing magnitude and direction. Say velocity is Vi at some instant, some delta t later, it is Vf. The particle is moving along a curved path, and well, to find the change in velocity, we'll draw these vectors Vf and Vi with their tails touching, and this will be delta V now. This is the magnitude of change in velocity, delta V. Well, now our interest is to find instantaneous acceleration. What we could do is this. From Vf, let's cut off a length equal to Vi. This is Vi. So this will be delta V, change in magnitude. This delta V, change in magnitude of velocity. And this is the magnitude of the change in velocity vector. So we cut off from Vf a length equal to Vi. This is the magnitude of the change in velocity. Change in magnitude of velocity. This is change in magnitude of velocity. This is the magnitude of change in velocity. I hope you appreciate the difference. Now anyway, this if this angle through which the velocity vector is turned is say delta theta, this would be this is Vi, right? This length is Vi. We have cut off a length equal to Vi there. So this length will be Vi 2 Vi sine delta theta by 2. That divided by delta t will give us the magnitude of the acceleration along this line. So this acceleration we calculate is along this line. So this acceleration is along this line, and this is about the change in direction. We cut off from length Vf a length equal to Vi. So this is about the change in direction. This would be as delta theta tends to 0. This angle, which is 90 minus delta theta by 2, after all, sum of these three angles is 180. These two will be together 180 minus delta theta, and half of that, 90 minus delta theta by 2. Right? So as that angle tends to 0, as delta t tends to 0, delta t tends to 0, delta theta tends to 0, this angle tends to 90. So this will be normal acceleration in the limit. The acceleration perpendicular to the velocity vector, a normal acceleration, this Vf tends to Vi. So And so it doesn't matter whether we have VI or VF here, because they're very, very close to each other. And sine delta theta by 2 becomes delta theta by 2. Sine delta theta by 2 becomes delta theta by 2. That 2 goes away. So this is VI delta theta by delta t, which is VI. Well, as the angle tends to 0, this delta theta by delta theta can be replaced by delta t tends to 0 here, right? This is what we are interested in, as delta t tends to 0. So this is VI delta theta by 2, that is VI omega, that is the rate at which the vector is rotating. Now this part, which is VF minus VI, as delta theta tends to 0, we are dividing this VF minus VI by a very small interval of time. We are talking a very small interval of time, so as delta t tends to 0, this becomes well, delta V by delta t, and this is what we call tangential acceleration. This is the normal acceleration and this is the tangential acceleration. This is our dV by dt, delta V by dt, and well, this is the instantaneous acceleration. This is along the tangent. So two accelerations here. So in the limit, this is what we have. This is VI, that's V. Again, there is no VI and VF because we are considering an interval of time which tends to 0, and we then call it an instantaneous velocity. So we can drop this subscript and say V. There is a normal acceleration like this, AN, and there is a tangential acceleration like this. You should be able to see how we get here from here. This delta theta, as it goes to 0, we cannot any longer see VF and VI separately. But this calculation, something very small by something very, very small, gives you a finite value. That's the whole trick of calculus. And this is the same technique. This is very small, and this is going to get very small, tend to 0. That divided by something which tends to 0. That delta t also tends to 0. This is what we get. Let's consider one other case of a particle going around a circular path. If this is the position vector of the particle going around a circular path at some instant, say it's going around in a circular path with a uniform angular speed. This is the position vector some time later. This is Ri, this is Rf, and the change in this vector is, this is delta R. This is Rf bar, Ri bar, this is Rf bar minus Ri bar, that's delta R bar. If this angle at the center is delta theta, this is an isosceles triangle, and if you drop a perpendicular and then find out the length of that, this, both of them are equal in magnitude, that's R each. So this comes to 2R sine delta theta by 2. This divided by delta t will give us the average velocity. This is the rate of change of position vector. And that average velocity vector will be along this tangent, right? So as the angle delta theta tends to 0, as delta t tends to 0, we'll have delta theta tending to 0. So this vector gets to be very small. This difference becomes very small. That divided by something very small, delta t, will give us the finite value, and that would give us instantaneous velocity, that is 2r sine delta theta by 2 when delta theta is very small. Let's call it d theta. This is d theta by 2 by dt. This is r d theta by dt, and that is r omega. This is the rate at velocity position vector changes. Mind you, this is the position vector, and the rate at which it changes at right angles to the length of that, right? So this is change of direction we are dealing with here, and if this vector rotates, we have rate of changes omega times r, where omega is the rate at which the vector is rotating. You can also express it in a vectorial fashion. V bar is equal to omega bar cross r bar. Well, there are three mutually perpendicular vectors here. R bar is this way. Omega bar is out of the plane. It's going around in the anticlockwise sense. It's out of the plane. And so omega bar cross r bar is along the tangent. That's the positive tangent. So this is the rate of change of position vector, that is, as the position vector rotates, constant magnitude rotates, the rate of change is at right angles to the length. We will consider a particle going at a circular path with a increasing speed. Say if you consider the position here, say the velocity is some vi, and some time later it is vf. Vf is greater than vi. This angle is delta theta. So this is vi, this is vf, this is delta theta. We've done this earlier. To find the change, we'll break it up into two parts: change in magnitude, change in direction. This angle is delta theta, so we'll cut off from vf a length equal to vi. We just did this a little earlier. So this is vi. So this is vf minus vi. That divided by delta t will give us the acceleration parallel to this line, and that calculation we're going to do when this delta theta tends to 0. So you're going to get, this is vi sine delta theta by 2, twice that divided by delta t. That's the acceleration normal to this velocity. We'll call that a normal, and that when you do the calculation for large delta theta, well, we'll have a certain average value. But when delta theta tends to 0, when delta t tends to 0, delta theta tends to 0, this will be vi d theta by dt, and this is instantaneous acceleration. Vi omega, we can drop that subscript. Well, this is what we got earlier. And this part, delta v by delta t, is the tangential acceleration. So we want to see it here as the angle tends to 0, this point moves close to this. There will be an acceleration parallel to the tangent. That will be vf minus vi by delta t as delta t tends to 0. That is tangential acceleration. And the other is normal acceleration perpendicular to vi, and that will be v times omega. So two accelerations, normal and tangential, when a vector changes magnitude and direction. Change of magnitude is taken care of by the tangential acceleration. Change of direction is taken care of by the normal acceleration. In this case, we call it centripetal acceleration. So that's it. So in general, if a vector a bar rotates at omega bar cross a bar is the rate of change of that vector. This changing only in direction, not magnitude. If there is a change of magnitude also, then we'll have to consider another component parallel to that a bar. So that's it. This is about a vector which changes direction.